Hello, chemistry students. We're going to be looking at a couple of examples of significant figures. It's kind of a weird concept. You're seeing it in your chem class. You're thinking, oh my God, math is completely different, but it's the same math you've seen. It's just important that we look at significant figures with measurements. So we'll go through some examples. All right. So in the measurement 1.05 meters, there are 3 significant figures. All right. And the rules. Any number 1 through 9 in a measurement is significant, and any trapped zero, so see the zeros between a number 1 through 9 and a number 1 through 9, any trapped zero counts as significant, all right? 0.7, like we got a touchdown, right? But 0.7 inches, this measurement has only 1 significant figure. The leading zero is insignificant, does not count, does not contribute, all right? 3.890 times 10 to the 15th kilograms. This is in scientific notation. We like scientific notation. This has 4 significant figures. Anytime you have scientific notation, everything in the first part before the times counts as significant. All right? In 0.01380, all right, 0.01380 grams, this measurement has 4 significant figures. Now there's a couple things going on. There are leading zeros. They don't matter. We start counting at the 1. We have the 1, the 3, the 8, and we have a trailing zero with a decimal point, which means this was measured. So this gives us 4 significant figures. The last measurement, 96,000 feet. This would be only 2 significant figures. It's only 2 because those trailing zeros are insignificant unless we put a decimal point there. If there was a decimal point, then this would read 5 sig figs, but there's no decimal point, only 2. What these significant figures tell us is the certainty in our measurements. We're certain of the 1, we're certain of the 0, we're not so certain of the 5. Right? We're never certain of the last significant figure. We're not so certain of this 7 in the 7 inches. We're not so certain of this last 0 in the 3.89 times 10 to the 15th. All right? We are not certain of this 0. We're certain of the 1, the 3, and the 8. And we're not so certain of this 6. So now we're going to do a simple density problem, right? Density equals mass over volume using 2 measurements, and we're going to round our answer to the proper number of significant figures. Mass divided by volume. Mass has 4 sig figs. The volume 47.0 is only 3 sig figs. Our answer is only as good as our weakest measurement, which is the 3 sig figs. So we're going to do 58.93 grams. We're going to divide by 47.0 milliliters. All right, we're going to punch that into the calculator. I'm going to put the whole answer first. Calculator gives us 1.253829787. All right, we have to shorten this answer. We have to round it. We have to round it to 3 sig figs to represent the 47.0 measurement being less precise. All right, so we want to keep 3 sig figs. So we're going to keep the 1, and we're going to keep the 2. We're going to look at the 5. All right, everything else is gone. But I want to keep that 3 there for a second. We know rounding rules. We've learned this before. If it's 4 or lower, we keep the number the same. If it's 5 or above, we would round up. So since it's 1.253, that's not enough to make us round it up. We're going to shorten our answer to 1.25 grams per milliliter. This would be the proper density with proper significant figures. All right, 1.25, 3 significant figures. That 5 we're uncertain of. Maybe it should be a little higher, maybe it should be a little lower. Any possible errors go back to our measurements. But these were pretty good measurements. 3 sig figs is pretty good. All right, so those are the rules for sig figs. We'll keep using them in class. You should be getting pretty good at it in a couple of days, all right?